Welcome! Today we are going to talk about one of my favorite things, solving by completing the square. All right, so what we're going to do here is, start by doing this investigation. So I want you to go ahead and solve this with square roots. So what you're going to do is you're actually going to take the left-hand side here and factor it, and then you'll get something that is square rootable, and then you'll be able to go from there. So go ahead, take a second, and let's get started. All right, so what we're doing here first is what's known as a perfect square trinomial, right? So in a perfect square trinomial, we have a squared plus 2ab plus b squared. Really, I'll put a plus or minus here because it could be a negative sign too, right? The last one's always positive, and it's going to factor as this a plus or minus b quantity squared, depending on what the sign was on that middle term. So this is going to factor as x, keep the sign the same, minus 3 quantity squared equals 1. And that factors so nicely here. Let's just take a moment for that. All right, so now let's go ahead and square root both sides. So I'll get x minus 3 is equal to plus or minus 1. We can add 3 to both sides, and we'll get x is equal to 3 plus or minus 1, which means that x is 2 and 4. So I want to draw a picture really quick of what's going on here. So let's say that I have this algebra tile here. Let's pretend I drew a square. Doesn't even look close. Let's try. Oh well. Alright, I'm spending way too much time trying to make that look better. Anywho, let's pretend that's a square. So what we're doing is, if I have this x squared, if the area of this is x squared, that means that this side length is x and this side length is x. All right. Well, let's say I have 6 x tiles and they're negative. So I'm gonna divide them up so that here I'll have 3 of them here, and I'll have 3 of them here. These guys, their area is x, and so their side length here is 1, and so if there's 3 of them, this is going to be plus 3, and this will be plus 3. So what we're doing here is the perimeter of this whole big square, let me outline this in black, can be, I guess, a perimeter. So the area of this whole thing can be written in 2 ways, as length times width, which in this case is x plus 3 times itself, or x plus 3 squared, but we can also write it as a sum of all the things in here. So this x squared, those 6 x tiles, which ours were negative, so I'm going to put, well, I already went into, I decided we're going with positive, so anyways, when I drew my thing and I forgot. Anyways, here we go. Now, what about this pink here? Well, if these tiles are all 1 unit long, that makes these each one unit. And so how many of them will there be? These are 1 unit squared. How many of those will there be? Well, 3 by 3 or none. So this is a perfect square, kind of more of a visual for you. So because this equation that we are dealing with factored as a perfect square trinomial, right? It's a perfect square, just like 4 is a perfect square, just like 16 is a perfect square. We can use square roots to solve. Well, that is so nice. Being able to solve with square roots, like I have said before, it just feels really intuitive, right? Because it's the inverse of squaring. So why can't we do that more often? So today we are going to manipulate situations so that we can solve with square roots by completing the square. So if we have an expression that does not factor, so we, right, can't use square roots the traditional way because we have a linear term, but we can't solve by factoring because it doesn't factor. What are we going to do? So this is where we're going to go about the process called completing the square. We are going to create a perfect square trinomial through this process that is called completing the square. What that means, right, is we're going to figure out what is this new perfect C value, perfect amount of constants, or these pink squares that we had, the unit tiles here, that will fill that in to create a perfect square trinomial. All right, so I'm going to give you all the steps first. It might not sound great until we go through our first example, so just bear with me. So the first thing we're going to do is move the old C term to the other side. So this C is what's standing in the way of our equation being a perfect square trinomial. And so we are going to get rid of it by moving it to the other side of the equation. If A is not 1, so our leading term is not 1, we're going to divide both sides of our equation by that A value to make it happen. Then we're going to create the new perfect C value, thinking about that pink square made up of the unit tiles. And this is going to be found by B over 2 squared. So what this means is it's going back to the fact that we have this 2AB in the middle as our middle term, right? So we know that whatever our middle term is that's in front of x, we want to divide that by 2 to get rid of the fact that we had 2 middle terms that were identical. And when we square it, that'll be our perfect constant that's going to make this a perfect square term. If you want to go back and look at the visual, right, if I have 6 x tiles, notice how they're divided into 2 sections. One section across here and one section across here, right? That is the dividing by 2. And then it's squared, right, because we're looking at the area here, right? This is half of B, or 3 in this case, and this is half of B, or 3 in this case. So when we multiply those together, that's how we get the square. All right. So once we have manipulated the situation, so we have this perfect square trinomial, the whole goal of that was that it would factor as one binomial squared. So we're gonna factor the expression. All right, after we factor the expression, the reason we wanted to do that, why we wanted it to factor something, one quantity squared, is so that we can square root both sides. Not forgetting plus or minus, of course. Then we're going to solve for x and y if necessary. Right? Sometimes there's a lot going on into that radical that we have to deal with, or maybe there's a radicand that has perfect square factors. All right, so what we've got going on here is an expression that does not factor. And so we're going to start by getting rid of this c value. This 30 here is making it so that when we go to factor this, that's not a perfect square. It is not helping us get 2ab in the middle, so that guy's going away. Now, this is where we're going to add our new perfect c value, right, which is going to be b over 2 squared. So in this case, it's going to be negative 10 divided by 2 squared, or negative 5 squared, which is 25. So I'm going to add 25 here. I'm going to add 25 on the right-hand side as well, because if I add it to the one side, I got to add the other side to keep this thing balanced. Now, remember, the whole goal of that was that it was going to factor as one binomial squared. So this is going to look like x, keep the first sign, minus 5, the square root of 25, and that's going to be equal to negative 5. All right, now we're going to square root both sides of the equation. We'll end up with x minus 5 is equal to plus or minus I radical 5. And then last but not least, we're going to add 5 to both sides, and we'll end up with x is equal to 5 plus or minus I radical 5. Beautiful. And look at that, we got some imaginary solutions even. Good stuff. All right, I know that was a lot, and I promise you it gets better the more we keep at it. So let's do another example. I've got x squared plus 6x plus 5. Now, let me tell you a secret. This one factors, okay? But I wanted to give you one that didn't have a bunch of radicals in it, so we can practice the technique anyways. So let's go ahead, subtract 5 from both sides. We're going to have x squared plus 6x is equal to negative 5. Now remember, we have to find b over 2, or half of b squared. So this is going to be 6 over 2 squared, which is 3 squared, or 9. I'm just going to add 9 over here. I'm going to add 9 over here. All right, the whole goal, right, the whole reason we're doing this is so that it factors as one binomial squared. So this is going to look like x plus 3 quantity squared is equal to 4. All right, now let's go ahead and square root both sides of the equation. We're going to have x plus 3 here is equal to plus or minus 2. Now we're going to subtract 3 from both sides, and we'll have x is equal to minus 3 plus or minus 2. So negative 3 minus 2 is negative 5. Negative 3 plus 2 is negative 1. So like I said, we could have factored that, but I wanted you to be able to see what it would look like with some nice rational solutions, and also so you can see that this works all the time. All right, next, got x squared minus 8x plus 11 equals 0. All right, we are going to, what do I do? That's right, we're going to move that 11 to the other side. Get rid of it. It is really ruining this for us, making it not perfect. We're going to add that half of b squared, which in this case is going to be 16 to both sides. We know that this is going to factor perfectly as one binomial squared because we manipulated it so that it would happen that way. So we've got x minus 4 quantity squared here is equal to 5. All right, so we're going to square root both sides here. We're going to have x minus 4 is equal to plus or minus radical 5. And we'll add 4 to both sides. So we'll get x is equal to 4 plus or minus radical 5. Okie dokie. Go ahead and try this one, guys, on your own. This x squared minus 4x plus 7. I know what you're thinking. But you've got this, I promise. All right, welcome back. Let's go ahead and solve this one. So we're going to subtract 7 from both sides. We'll get x squared minus 4x equal to negative 7. We're going to add half of negative 4 squared to both sides, which is going to be plus 4. This is going to factor perfectly as x minus 2 quantity squared is equal to negative 3. We're going to square root both sides and say x minus 2 is equal to plus or minus I radical 3. And we'll add 2 to both sides. We'll get x is 2 plus or minus I radical 3. All right, this last one, I'm going to show you a bit of a gnarly case, right? It gets kind of ugly, but it's going to teach us some good lessons about when we might want to ideally use complete the square and when we might not. So let's go ahead and subtract 6 from both sides. So we'll get 3x squared minus 5x is equal to negative 6. Now notice that the a value here is not 1. So we need to divide both sides by 3 because this technique only works when the a value is 1. So we're going to have x squared minus 5/3 x. Yep, everything gets divided by 3 is equal to negative 2. All right, well now we have to find b over 2 squared, right? So we're going to have negative 5/3, right, times a half, and then we're going to like square that. All right, so it's going to be 5 over 6 squared, which is 25 over 36. That's our magic c value here that we're going to add to both sides. Not horrible, I promise. All right, so now this still factors perfectly. It's one binomial squared. We'll have x minus 5 over 6. Over here, this is going to look like if I add negative 2 plus 25 over 36, I'm going to get negative 47 over 36. I'm going to square root both sides. bracket x minus 5 over 6 is equal to plus or minus I radical 47 over 6. Right, so I took the square root of the denominator. 47 has to stay under the radical, but I was able to take out an I. Then I'll add 5 6 over. So this will look like 5 plus or minus I radical 47 all over 6, since those had a common denominator. It's not the prettiest looking answer, but it's the right answer. And also, there's 2 of them here, right, because of that plus or minus. So this answer is going to be what our answers are going to start looking like when we use the quadratic formula in our next lesson. But yeah, there you have it. So this is kind of teaching us a little bit. We probably want to reserve using completing the square for when we have an a value here that's 1 and an even b value, right? Because our b value not being divisible by 2 kind of stunk. All right, so there's that. I hope that this was informative and now you're feeling so much more confident in your ability to solve quadratics by completing the square.